All right, everyone, welcome to our 13th SI session. Today we're going to be looking at some more impedance concepts, and we're going to get into some problems a little bit later. Okay, so let's look at a few new concepts, VRMS and IRMS. So RMS stands for root mean squared. So what does this mean for us? Well, if we're looking at a graph, and I want to do this in black, our VRMS is going to be the square root of 1 over the period integral 0 to the time period. We're going to integrate the voltage with respect to time squared. So that's the graphical method. VRMS is also equivalent to the magnitude voltage divided by the square root of 2. And you're going to see this form quite often. Okay. Looking at IRMS, very similar. The graphical form. IRMS is going to be square root of 1 over period, 0 to the period. Now it's going to be I squared as a function of time integrated with respect to time. And very similar to VRMS, IRMS is going to be the magnitude current over square root of 2. Okay. So just general equations, and these are very important. We're going to see these going forward. Yeah. We're going to take a look at average and effective power. So these are just kind of different ways of representing the same concept. So if you see P average, P effective, it's going to be V squared RMS over R, or I squared RMS times R. Okay, and these look very similar to what we've worked with in the past, where we just did power is equal to V squared over R, which is just equal to I squared R. So same form, just using the RMS values now for the impedance values. Okay. Let's take a look at some of the old methods that we've been working with the new forms. So complex, phasor, rectangular forms. So KCL, complex impedance. So this is where we're going to have I1, I2, I3, and then we're just going to sum those currents entering and leaving. So we can say negative I1, negative I2 plus I3, that'll be equal to 0. So this is just representing the sum of the currents is equal to 0 at the node. So these are the same rules as before. Okay. Let's go and take a look at the KVL complex impedance. So here, we'll go ahead and draw out just a quick schematic for us. That'll be V1, this will be V2, V3, and this will be Vs. Okay. Where just like the KVL, we'll walk this loop as if this current was here. And all we're going to do is assign whatever terminal sign that we see to these voltage values. So negative Vs plus V1 plus V2 plus V3 is equal to 0. So we're just saying here the sum of the voltages is equal to 0 in a loop. Okay. So node, loop. So these are just the same rules as before. also. But keynotes, these are all in complex phasor or rectangular. Okay. Same deal with down here. So complex, phasor, rectangular. Okay. So we're just treating them the same way as we did before with just resistors, but now we're going to be using the X and Y values, the real and imaginary values. And we're going to see some of those applications here in just a minute. All right. Well, that does it for the concept video. I will see you in the next few videos working some of the rest of the problems.